Hello and welcome to this webinar. My name is Iqbal Singh Josan and I'm going to present this webinar today on MIMO in 4G wireless. During the webinar, you can ask me a question by typing in the chat box on the left side at the bottom of the screen. This will allow you to interact with me. If you have any question, just type in the text in the chat window and I'll respond to you. Thank you. So let's begin now. Well, here is the outline of various topics that we are going to cover today. We'll introduce ourselves to MIMO technology, understand how it works and how the benefits from MIMO, mainly higher throughput and reliability, are realized in wireless broadband infrastructure. We will examine how wireless throughput can be multiplied and how the wireless connection, the over-the-air link, can be made more robust and reliable by using antenna diversity, beamforming, and STM. Now, STM here stands for Space Division Multiplexing. Then we will talk about how MIMO is used in various wireless broadband standards that includes Wi-Fi, WiMAX, and LTE. Finally, we'll have a glimpse of the future of MIMO and see where this technology is going. So MIMO basically stands for multiple input and multiple output. What that means is multiple transmit and receive antennas, and that implies multiple radio channels between the transmitter and receiver. So the term input and output here refers to the radio channel and not the devices themselves. What that means, we have multiple signal inputs into the radio channels at the transmitter and multiple outputs taken out of the radio channels at the receiver. So as you see in the figure here, 1, 2, 3 up to M are the transmit antennas and 1 to N are the receive antennas on the right side. And there are multiple radio channels, or we can say communication paths between the transmitter and the receiver. You can see in the picture there's a path from 1 on the transmit side to 1 on the receive side, or 1 on the transmit to N on the receive side, and so on. So you look at the picture, this is how the real life MIMO transmitters and receivers look like on our devices. So some of you may have seen them in the stores. So as time goes by and MIMO is adopted everywhere, you will see more of them. So let's go back a little. What came before MIMO? What is the predecessor of MIMO? Well, before someone had even heard of MIMO, and from the time wireless communication began, we had SISO technology, which is a single input and single output. In other words, a single radio channel and a single communication path. So all of us have used it and even using it now in second and third generation mobile phones. In fact, SISO is the most commonly used transmission mode. So does this picture look familiar? You must have seen these microwave dish-like antennas on cell towers. These provide communication links with the core network or with other cell towers and are point-to-point links. So this is essentially a SISO system, single input and single output. Then from SISO, we evolved to a SIMO system, which is a single input but multiple output. What makes this system work? By having multiple antennas at the receiver pointing in different directions, I could take advantage of the multipath propagation of radio waves and therefore add to my signal strength, increase my signal to noise ratio, make my signal more reliable and robust, and so on. So in real life, you see in this picture, I have a radio signal received directly from the transmitter. Then I have another one from a tall office building, which is a reflected signal. So the signal from the tower first strikes the building, and from there it's reflected and then received by receiver. And a third copy of the signal reflected from the hilltop. all signals arriving at my SIMO receiver, which has multiple antennas on the receiver side with different signal strengths and phase responses. A SIMO system can help me get the best out of a combination of 3 copies of the same signal. We'll see how a little later, how we can make use of these 3 copies of the signal for our benefit. Then we move on to MISO, which is a multiple input and single output, the multiple input and single output system, where the receiver, such as my handset or cell phone, has a single antenna. Most of us have a single antenna cell phones these days, right? But I have the luxury of 3 radio channels transmitted from 3 different antennas on the transmitter side. So does it sound like I have some redundancy or backup radio channels available? Well, that is true. And this can help me make my signal transmission more robust. If I lose one signal, I have another signal which I can use to receive data from the same transmitter. So this is the real life picture will look like. You will see cell towers with multiple antennas. And if they implement MIMO, yeah, my cell phone can tune into one of these signals. If the one signal fades, the other one can be used as a backup. So that overall I have more reliable signal. I can combine these multiple signals to increase my signal to noise ratio and my signal strength. So I can overcome my problems of fading and broken voice calls and broken links and so on. So finally we arrive at MIMO, where I have even more luxury of having multiple antennas at the transmitter as well as receiver. So I have multiple radio channels available that can help me add more capacity, in addition to making my communication link more robust. So think of like this: if you have a wired Ethernet link to your PC, a single wire connecting your PC to the network. Imagine if you had like 3 or 4 wires connected from your PC to the network and each adding to the capacity, to the data that you could transfer. So here, instead of wires, you have these 3 or 4 separate radio beams between the transmitter and the receiver. That will add to the capacity and make it more reliable too. Now, before we move on, I would like to pose an interactive question. Which antenna configuration is depicted by the figure on the screen? Is it a SISO, a SIMO, a MISO, or a MIMO? So take a moment to think about this scenario, and you can write the answer number in the text box and send it to me. Which one you think is the configuration displayed here? Well, thinking. Well, the right answer is number 1. It is a SISO system. Why? As we discussed before, the terms input and output refer to the radio channels. Although you see multiple receivers in the picture, but each receiver has a single antenna input. So a single input is going to the receiver, each receiver. If you look at other way, the transmitter is pumping in a single channel of television transmission or data transmission into the radio channel, and each receiver is checking out just one output from the channel. It is a SISO. Yes, some of you have answered it correctly. Very good. So let's move on to the next slide. So looking at all this, what we have seen so far, let's see what all promises we have from this technology, MIMO. What do we get out of MIMO by having multiple antennas at the transmitter and receiver? That adds more complexity to our wireless system design. However, well, but what are the benefits? So many of us are familiar with the effects of fading and multipath interference that we have to contend with in a wireless communication link. Remember, whenever you're trying to make a call from your mobile phone while driving, and sometimes the signal will fade. Your phone shows only a single bar of signal strength and the call drops. Also, even on a third generation phone, a video download could be very frustrating. Well, with MIMO, you have the promise of a robust radio channel. The effects of fading and multipath interference are mitigated. You can forget breaks in voice calls or data, higher throughput, faster downloads, more megabits per second. In other words, more bang for the buck. You get more bandwidth with the same amount of money you spend every month. And on top of that all, it enables 4G wireless broadband applications in different standards. In wireless LAN standards, which is 802.11 family of standards, the version N and AD, so these have adopted MIMO. N is commercially available, AD is not yet available, it's going to be. WiMAX, which is IEEE 802.16m, has also completely embraced MIMO. LTE Advanced, which is 3GPP release 10 standard for cellular communications, has a MIMO specification. Release 12, which is currently being drafted, it has a full-featured MIMO available. It will be available soon within next year or couple of years. So MIMO is going to be everywhere, in other words. So let's see what other details are there we need to learn from MIMO. So yeah, the picture here shows a picture of a handset might look in the future. It may not look like exactly like that, but the idea is that your cell phones may have multiple antennas in the future. Instead of single antennas we have right now, soon the technologies will become mature enough to have multiple antennas, which will have a gigabit per second capability to download data. Okay, let's hope for the best. So how do we realize all these promises from MIMO? What are the techniques which are used? So basically there are three main techniques. One is the antenna diversity, which may be on the receive side or transmit side. That means more antennas, not just single antenna, but more antennas. Then second is beam forming, how we can control the way we form the radio beam. And then the third one is space division multiplexing, and how we use the space resource for multiplexing different signals. So we'll discuss each of these in a little more detail in coming slides. So before we go into that, let's understand a little more the multipath propagation. This is a fact of life. Radio waves, you don't get a single signal, you get multiple signals. One coming straight from the transmitter, others which are reflected. So in the picture you see a mobile receiver that is receiving radio signal from three different paths. One is direct line of sight, other two are reflected from a tall building and a hilltop. So these signals propagate along paths of different lengths and may arrive at the receiver with different amplitudes and phases. If the signals are in phase, they will add up. And if they are 180 degrees out of phase, they will cancel out. So you see the picture. If they are in phase, they will add up and add to the signal strength. But if they are out of phase, you get no signal. But as the mobile station moves about, we keep moving with our cell phones, right, most of the time. So the phases of various paths vary in a random fashion. Since there are in reality several propagation paths, they rarely cancel out each other completely. But all this ultimately leads to a drop in signal level of 20 to 30 dB, and it causes fading. Your signal fades ultimately. So this is a known problem, a nuisance sometimes. We are in some important call, and because of this multipath propagation, different signals canceling out each other or adding to each other in a random fashion, they lead to multipath fading. Now in digital signals, cell phones have digital signals, right? There is one other problem, is inter-symbol interference. because we are ultimately receiving streams of data from our transmitter, right? So what happens, all these three signals which are coming from different paths, the symbols interfere with each other. As you see in the picture, symbol 1 and symbol 2 on path 3. Then on path 2, we have symbol 1 arriving late and interfering, portion of it interfering with symbol 2, which is received from path 3. And also a portion of symbol 2 interfering, which is delayed copy of symbol 2 interfering with the one received on path 3. Now this can be a bigger problem. What this means, if we are receiving data over the air and all this thing is happening due to multipath propagation, the receiver will see the adjacent symbol superimposed and it will appear as useless or corrupted data bits, will miss data. So the challenge for a mobile wireless system design is to remove or avoid the ISI, the inter-symbol interference. Okay. So now we come to the basic techniques that we use with MIMO. The first one we take is receive diversity. So one solution offered by MIMO is receive antenna diversity. What that means, deploy multiple antennas on the receiver spaced at least half wavelength apart and combine the signals from these antennas in such a way so that signal to noise ratio is enhanced at the receiver and the effects of multipath fading and ISI are mitigated. Well, keeping them half wavelength apart minimizes the correlation between the three received signals and creates relatively independent paths to and from the different antennas. Well, the antenna configuration you see here is essentially a SIMO configuration, which can be considered as a special case of MIMO. Now, there are different ways to combine the signals from these multiple antennas on the receiver side. One method is selection combining, which uses a switch essentially to select the received signal with the maximum signal to noise ratio. So what I basically do, I look at the three signals. The circuitry inside my receiver actually is designed like that. It looks at three signals, and the one with the maximum, the strongest signal I select. And the strongest signal fades, I look at the second signal, which is the strongest available, and I pick up that one. Because all signals have copies of the original data coming from the transmitter. So other method is equal gain combining, where actually I use an equally weighted combination of all received signals. So I take one third of the first signal, one third of the second, and one third of the third one. And another way I could use is maximal ratio combining, which uses a weighted combination of the received signal based on signal to noise ratio. So the strongest signal has more weight and the weakest has the least weight. So it depends on the carrier or agency who is implementing this while designing the product, and which type of combining gives you best results for that particular application. Next, we move on to the transmit diversity technique, where we deploy multiple antennas on the transmitter. The antenna configuration is MISO in this case, which can be considered as a special case of MIMO. So this technique can prove to be more practical in cases where, because of the form factor of mobile handheld wireless devices, it is often not possible to deploy multiple antennas on the receiver that are half wavelength apart. So what do we get out of transmit diversity? We have multiple transmitted radio beams, one from each antenna, that can be spatially distinguished. Each radio beam carries an identical copy of the signal. Space-time block codes, these are special codes used to insert time delays in the transmission paths so that individual signals can be separated. The time delays can typically range between 50 and 200 nanoseconds. So the benefits here are improved signal to noise ratio and reduced effects of multipath propagation, namely faded signal and ISI. So here you see a pictorial representation of how the three different radio beams are transmitted. We purposely insert a time delay, and from how much time delay we inserted in there, we recognize the beam, that this is a beam separate from the other one. That is how the space division multiplexing actually works also, as we see in a later slide. Now let's hold on for a while, and I like to pose a question again. So what is not a benefit of antenna diversity? Is it diversity gain? Is it enhanced signal to noise ratio? Is it increased bandwidth? Is it redundant copies of signal? So again, please type your answer in the chat window. Take a moment to think about this. Well, yes, the right answer is number 3, increased bandwidth, which is not a benefit of antenna diversity. All the other 3 are benefits. We get diversity gain, we get enhanced signal to noise ratio, and we also have redundant copies of signal. Well, moving on to next technique that is used in MIMO, beamforming. So in beamforming, we basically control shape and direction of radio signals. So this can be realized when we have multiple antennas or an array of antennas. This technique is used to control the shape and direction of transmitted or received signals. It combines signals in antenna elements in such a way that constructive interference happens in a certain direction and destructive interference happens in other directions. So beamforming can be used to extend the range of signals in a certain direction, such as towards a highway where density of mobile users is more compared to other directions. So you see in the picture that the radio beam is steered towards the receiver in a different direction. This is a valuable technique for commercial carriers and allows them to increase user coverage by focusing radio beams on areas that have the desired user population. Or you could direct the beam toward a user population where density of mobile users is more compared to other directions. In other words, the beam can be steered in the desired direction. Now this would not have been possible with a single antenna. You need multiple antennas to control the direction. And MIMO makes it possible. Now, next technique we use in MIMO is space division multiplexing, or SDM in short. So space division multiplexing is used to achieve higher data rates instead of signal quality. So it works well when signal to noise ratio of the channel is high. In other words, the data carrying capacity of the channel is high. Therefore, multiple data streams can be sent over spatially separate radio beams, but over the same RF bandwidth. Remember, MIMO does not need more bandwidth or more power from the transmitter. It simply uses additional space which is freely available. So SDM does not exhaust the frequency resource, but uses space as a resource by exploiting different directional beams that can be sent from an antenna array. So in the picture you see M by N MIMO. That is the convention that is used to write the configuration of MIMO. So M represents the transmitter number of antennas, and N is the number of antennas on the receiver side. Like if you have 4 antennas on transmitter and 3 on receiver, it's called 4 by 3 MIMO, and so on. So let's find a little more about how this SDM works. So in SDM, we have signal path coefficients, which are shown like H11, H22, H12, and so on. It's a matrix representation and up to HMN. So these coefficients represent actually amplitude and phase response for each signal path. So each signal path will have a specific signal path coefficient defined. Now, how do we determine, this is a physical channel. So there is a training sequence which is initiated before a transmitter and receiver can even exchange any data or information. Like you switch on your MIMO phone and try to connect to your MIMO transmitter, the first thing that will happen is a training sequence. That means both transmitter and receiver will try to find what all beams are available between them. That is called a training sequence, and all wireless standards have a specification for training sequences. So typically, transmitter generates a known training signal, which is known to the receiver also in advance, and receiver processes that signal to estimate path responses. For each beam, it will estimate what is the amplitude and what is the phase response. And based on this, while it is scanning these beams, it will build a matrix. That matrix will be used for computation of received signal at a later stage. Like this is a MIMO channel represented as a matrix of signal path coefficients. It's represented by H, and the equation is like R equals H multiplied by T. T is the transmitted signals and R is the received signals. And if you want to derive the transmitted signals, that the signals that were transmitted, so the receiver will use this equation, take an inverse of H, multiply with the received signal, what it receives on the receiver side, and then you deduce the transmitted signal from that. Now, this is a very high-level simplified representation of MIMO. So in actually the signal processors on the transmitter and receiver side, they actually compute this matrix. They measure the signal coefficients and then measure the received signals, do this computation, and then arrive at what signal received. And from there, you get the signals. Now, let's stop for a while and have another question. So which technique will you recommend when the radio channel is very noisy, when the signal to noise ratio is very low? Do you recommend space division multiplexing, or do you recommend transmit antenna diversity? Do you recommend space time block codes, or do you recommend time division multiplexing? Well, okay. The right answer is number 2, transmit antenna diversity. Why? So as we discussed before, antenna diversity provides diversity gain by improving signal to noise ratio. So remember, when signal to noise ratio is low, the first thing we have to do is improve the signal strength. And diversity techniques are the best bet for that. Space division multiplexing you will use when your signal is already very strong. The channel is very perfect, like you have a perfect communication link between the transmitter and the receiver. That means you can send more data, more throughput. That is when you use space division multiplexing. That is the ideal scenario for space division multiplexing. But for poor radio channel, when your signal to noise ratio is very low and the channel is very noisy, so then you will typically use the antenna diversity, have more antennas on the transmit side or on the receive side or both. Okay, so let's move on to the next slide. Now, there are a few terms we need to understand which are important for practical application of MIMO. One is the multiplexing rate. So in MIMO, multiplexing rate is defined as the number of distinctive data streams that can be received correctly and simultaneously. What that means, if for a thumb rule, like if you have a M by N MIMO, M cross N MIMO, it is the minimum of the two, minimum of M and N. Like if you have 3 antennas on the transmit side and 2 antennas on the receive side, then multiplexing rate is 2, the minimum of the 2. What this means, the higher the multiplexing rate, higher will be the throughput. So in any MIMO system, this is an index of how much throughput you will have. Like if you have, let's say, 4 cross 3 MIMO, then the minimum of these is 3. Then multiplexing rate is 3. That means you have 3 times the output. we have 3 times the throughput of a single antenna. So in addition to multiplexing rate, okay, before we move on, let's is the picture describing it in more detail. Now when we say multiplexing rate 2 here, so you see the receive side, you can receive 2 beams from any of the 2 antennas on the transmit side. So all these are different scenarios how the 2 beams could be received in this particular system, MIMO system. So next we need to understand the diversity gain in MIMO. What is it? So as per the definition for any narrowband system with slow fading, it's an estimate of the basically how we improve the signal to noise ratio. So it's mathematically it can be calculated by a product of M and N. So if you have 3 antennas on the transmit side or on the base station, and if you have 2 antennas on the receive side or on the user side, 3 cross 2, it's 6. So 6 indicates the diversity gain. What that actually means is that a diversity gain of 6 means that signal to noise ratio is improved by a factor of 6. So remember that now there are two parameters here. One is the multiplexing rate that in the previous slide we had multiplexing rate. That is a measure of the throughput. How much throughput, how much more throughput we have. So we take a minimum of the number of antennas and that is the multiplier for throughput. Now here when we multiply 3 cross 2 and arrive at 6, this is the diversity gain. That how many more antennas we have on both sides and how much diversity we have. Now let's move on to the next one. Now in a typical MIMO system, we'll have competing demands. On one hand, we want to increase throughput by having a higher multiplexing rate. And on the other hand, we also want to maximize signal strength and mitigate the effects of multipath propagation by having a higher diversity gain. Now you can't have both the best of both worlds. You have to have a trade-off here, a compromise based on what type of application I'm running. A trade-off is possible, so there are 2 cases here I'm showing here for trade-off. Let's consider a 5x4 MIMO, 5 antennas on the transmitter and 4 on the receiver. And let's assume in this case we want to have a reliable mode. What that means, reliability is of paramount importance. I want a reliable signal. I don't want to miss even a single bit. My throughput may be a little lower, but it must be very reliable. Let's say I want to have a secure communication. An emergency response team wants a signal that can be relied on. You know, when disasters happen, throughput is not very important. Reliability is. It must be reliable. So there are applications where reliable mode is needed. Now let's say I choose to have a multiplexing rate of 2. That means from this 5x4 MIMO, I am dedicating 2 antennas on the receive side and 2 antennas on the transmit side for throughput. My minimum requirements for throughput here are 2 by factor of 2. Then what I am left with on the transmitter side, I am left with 3 antennas, and on the receiver side, I am left with 2 antennas. So my diversity gain is now 3 cross 2 equals 6. That is a trade-off I do. By choosing a multiplexing rate, a lower multiplexing rate, I can have a better diversity gain or better signal to noise ratio and better reliability. Now let's have another case where reliability is not very important, but yeah, throughput is. I must watch this latest streaming movie, high definition movie from Netflix on my smartphone. So there may be some jitter sometimes, but who cares? Like as long as can we watch the whole movie. Here I choose to have a multiplexing rate of 3. That means 3 antennas on the transmit and 3 on the receive side I'm dedicating for throughput. So I'm left with what? Only 2 antennas on the transmit side and only 1 antenna on the receive side for diversity. So my diversity now falls to 2 cross 1 equals 2. So you see how the trade-off is possible between multiplexing and diversity combo. I could balance out the 2 things, the throughput and my reliability, which I achieve through diversity gain. So let's move on to the next. So now let's see how this MIMO works out in the real world wireless communication standards. Now in Wi-Fi, the N version has adopted MIMO. Diversity is up to 4 by 4. They support transmit beamforming. They support space division multiplexing. And there are two bands there, 2.4 and 5 gigahertz ISM band. ISM is Industrial Scientific Medical Band, which is a unlicensed band actually. And it allows 20 or 40 megahertz bandwidth. So physical data rates can be achieved up to 600 megabits per second, but ultimate throughput is more than 200 megabits per second. So why this figure is lower than 600? Because of the overheads. You have header information. See, there's some real data, then there's a header information. So there's too much header information more too. And you have some maintenance signals, some beacons going on. All those are overheads. And what MIMO does in case of Wi-Fi is it extends the range. The indoor range without any repeaters is extended up to 70 meters. And outdoor you can go up to 250 meters. So with MIMO, with just one access point, you could cover a whole building actually, right? Now let's look in little more detail into MIMO antennas in Wi-Fi. So we'll discuss how MIMO antennas are typically implemented in a Wi-Fi access point. So have you seen a narrowband monopole implementation? You must have seen some routers available which have at least 2 or 3 antennas. With 2 antennas is very common, but they have started coming with 3 antennas too. That is actually MIMO. And it comes with the N version. So here you see a narrowband monopole implementation where half wavelength separation is kept between antennas to reduce mutual coupling between radiating elements. So this is the easiest implementation. However, it is narrowband and has high profile. Now you can't hide it somewhere. It will be visible. You put in a room or install somewhere, it will be visible. So it has high profile. So if the separation between elements is reduced, then mutual coupling between elements induces large impedance at the feed. This will deteriorate impedance matching, radiation efficiency, radiation patterns, and diversity performance. So it is also difficult to ensure omnidirectional coverage in both azimuth and elevation planes with this type of antenna. But of course, they have started coming in this form. They are narrowband monopole, so something is available. So MIMO in Wi-Fi. But let's move to the next, where there is a design for compact access point antennas. So here you see a multi-band compact antenna design. Each element has an inverted F shape and has 2 parts. The left part is the 5 gigahertz antenna element and right part is for 2.4 gigahertz. So from the top view, you see there are 3 such slanted antenna elements spaced at 120 degrees apart to provide satisfactory omnidirectional and multi-band coverage. Like if you place this type of antenna in the center of a building, you'll get uniform signal everywhere in the building. So these elements are typically fabricated on a PCB that helps to make it compact and low profile. So you see on the antenna element, the 2 elements support both 2.4 gigahertz and 5 gigahertz frequencies. Now, antennas for portable devices. They are a little more challenge actually. When you come to portable devices like laptops, iPads, and smartphones, there are additional challenges. So antennas are packed with several other peripherals which are conductive and lossy, and it reduces the efficiency of the antenna. Therefore, there are trade-offs to be made between design, performance, and placement. The performance parameters such as operating bandwidth, impedance matching, peak and average gain, radiation patterns, efficiency, specific absorption rate are important. Also, the human body effects on the antenna need to be considered. So this picture shows a case 1 scenario where diversity is achieved by placing a second radiating element along the length of the ground plane. So you see the 2 elements, one is placed here on the side and one is placed here. Now this separation of antennas provides a good diversity of antennas. We have two antennas here instead of in the older design you had only one, but now you have two. So you have some MIMO functionality available here. Now sometimes, but you have to do a trade-off. You may not have enough space inside the device to place elements uh, two apart from each other. So here you could place them beside the first one. You would place the second antenna element beside the first one. So there is limited spatial diversity. However, the antenna feed points are much closer compared to case one. So although you sacrifice diversity a little in this case because the antennas are closer now, but you gain advantage in other ways, like your feed points are closer, so your losses due to feed points being far apart, they are reduced now, right? So again, it's up to the actual device, how you implement physically this design inside the device and which one is best for any particular device. But again, trade-offs are there. You have to trade off one thing with the other. Now let's stop for a moment once more. So what is the recommended physical separation between antenna elements of a MIMO system? Is it lambda by 4? That means quarter of the wavelength? Or it just depends on the wireless standard? Or is it a minimum of lambda by 2 or half wavelength? Or it does not matter? So what do you think? Well, the right answer is 3. So why? As we discussed before, to avoid mutual coupling between antenna elements, the physics is the physics behind it. The physics makes it minimum of half wavelength. So we have to keep it minimum of half wavelength, the separation between antennas, to avoid any mutual coupling and avoid any interference between one antenna and the other. Okay, let's look at how MIMO goes in WiMAX. So here the 802.16m version has full-featured MIMO. It supports all techniques: antenna diversity, beam forming, space division, multiplexing. And you have these frequencies which are country specific, 5 to 10 megahertz bandwidth, and it has enhanced throughput. Now it supports two different configurations of MIMO, SU or single user MIMO and a multi-user MIMO. We'll discuss in a little more detail what is the single user MIMO and multi-user MIMO. So next we come to LTE Advanced, which is 3GPP release 10. So this has also adopted full-featured MIMO and again supports all the three techniques, different frequency bands, which depends on the carrier, the country, and the region. Scalable bandwidth, 20 to 100 megahertz, enhanced throughput, 1 gigabit per second downlink, and 500 megabits per second uplink. Again, this MIMO in LTE Advanced also supports single user or multi-user MIMO. So what is this single user MIMO? So in single user MIMO, actually, one user gets the benefit of full throughput from the antenna. So you have 3 antennas on the base station and 2 antennas on the user equipment. And all data is transmitted from the base station to single user at any point of time. So if the throughput is 1 gigabit per second, all of it is claimed by one user. And this could have very niche applications. Maybe the military or the government will have such applications where each of their equipment needs very high bandwidths. Now in our commercial, so this is another picture that shows a single user, a real life single user device, which has 2 antennas and it gets the benefit of full throughput here. Well, then in multi-user MIMO, which is more obvious implementation of MIMO in the commercial world, multiple users share full throughput. Because in our cell phones, our smartphones, we may not need so much of throughput actually, right? If you have, as of the present scenario, if you have 15 megabit per second download speed, you are pretty much okay. Like you can watch streaming movies from Netflix and so on. So even single antenna devices are still there and they're going to be around for a long time. Single antenna devices are going to be there. All devices do not need very high bandwidth. So in this case, the present deployment, in fact, the present deployment of LTE that is happening currently in North America, in Asia and other places, it is actually multi-user MIMO, where the base station has so many antennas, I mean 4, 5, 6, because on a cell tower you can put many more antennas. But the user phones have single antennas, but all of them, they share the bandwidth. But as a end result, they get more bandwidth than they had before. Before, base station had single antennas, right, in transmitting signals in one direction. Now the base station has multiple antennas. Multiple antennas means it can deliver more bandwidth to each user, even though it has a single phone. So multi-user MIMO allows single antenna devices, which are actually several handheld wireless devices as of today, to share the same time and frequency resource to improve spectral efficiency and average user experience. So spectral efficiency actually means how many bits you can transmit to the device per hertz or per cycle. So we can, with this multi-user MIMO configuration, we can transmit more bits per hertz or per cycle of the frequency to the end user, and therefore improve the average user experience. So let's look at the future. Where is this technology heading? Massive MIMO. So massive MIMO means very large number of antennas at the transmitter and the receiver. In fact, there is a standard currently which is IEEE 802.11ad. AD is for advanced. It's called WiGig. It has adopted massive MIMO. So why is it possible for this standard to adopt this technology? Now, it operates in 60 gigahertz unlicensed band. So you have 4 channels of 2 gigahertz each, and up to 7 gigabit per second data rates. So 60 gigahertz frequency, that means your wavelength is only 5 millimeters. Your lambda is only 5 millimeters because the frequency is very high over here. It's 60 gigahertz. Now remember, earlier we discussed that the minimum separation between antenna elements must be at least lambda by 2. So in this case, the separation will be what? 2.5 millimeters only. If we have 60 gigahertz unlicensed band frequency, our antenna separation drops down to only 2.5 millimeters. And what that also means that it will allow us to fabricate antenna elements within a very small form factor, such as 1 centimeter square. A square of 1 centimeter can hold as much as 16 antenna elements, each antenna element separated from each other by a distance of 2.5 millimeters, because we are using 60 gigahertz unlicensed band. So just think about the consequences of this when we have so many antenna elements in a very small space. You could have smartphones with multiple antennas, maybe 16 or maybe even more. Smartphone has much more than 1 centimeter square of space. You could fabricate all these antennas into the physical body of the smartphone and have a MIMO smartphone, and also capable of multi-gigabit reliable throughput. In addition to this, you could also have base stations in smaller form factor, such as the size of a pizza box, that could pack 256 or more antenna elements. So just think about this, what all new applications could come out of all this by having massive MIMO. Now other standards are yet to adopt this. So IEEE 802.11 is the first one adopting this massive MIMO techniques, but soon others will follow as more new applications are conceived and deployed with massive MIMO in the coming years. Okay, so before we end the webinar, I'll give you a list of published material which you can use to dig deeper into this MIMO. You can refer these publications, and I'm going to send you a copy of these slides for your reference, which you can use at your own convenient time. And now any questions and answers? I'll be happy to answer any questions. I have a few minutes here. If not, then you can email me any questions you have at a later stage also, and I can answer your questions about MIMO, about this webinar, and about the this company, US Pertec LLC, about their what all services we offer. So it seems there are no questions at this time, but definitely I'll wait for any emails from you. If you have any offline questions, I'll be too happy to answer those. I'll be emailing the slides from this webinar to all of you. And then there's information to claim your professional development hour. As I promised to all registrants that they will achieve one professional development hour by attending this webinar and a certificate of completion. But there is a little requirement for that. So after this webinar ends, you will be redirected to a webinar forum page at bit.ly, that is ly /MIMO forum, where you will be required to complete a feedback form and respond to a problem statement from this webinar. It's a descriptive problem statement. You just have to respond in the comment box. And after these two things are done, your certificate of completion will be emailed to you within 2 business days. And on this slide, I have my contact information, my email ID, my LinkedIn profile, and my Twitter. Or you can also visit our website at uspertech.com to learn more about our upcoming webinars and on-site training services. So thank you for attending this webinar. Thank you. Bye.